All right, we're rolling for today's class. Before we dive into this class material, I wanted to just mention again that if you have your birds, then you can bring those in front of you. That's cool. If you are willing to show your screen, I appreciate that. I understand some people are not, or you're not in a position to. Sometimes I do that in meetings. But once again, just reiterating, I appreciate seeing your faces, and I do use that as feedback cues to figure out whether to keep going or change things. Second thing is, if you are finding that with COVID stuff going on, either your job situation's changing or whatever's going on, if you find that you have needs that you didn't before, whether that be financial or connectivity or resources, that kind of stuff, the university has set up some funds to try to address that, and there's some fundraising issues going on. So if you have any needs, I think we sent an email out to the student population, but I have a way to connect you as well. So feel free to reach out to me, and I'd be happy to get in touch with you. I don't know if bird sitters are one of the resources they provide, but they do have some other resources that may be useful to you all. So please let me know. Don't let things get to a point where it impacts your situation as class, if we can do something to avoid it. All right. I've already sent out the first clicker question. Hopefully you've seen it, and I am going to share my screen. Looks like one person to admit, and I'm going to go ahead and do our first clicker question. So go ahead, y'all, and I want you to look at these pairs of compounds and basically saying if we have a solution and we have the same number of moles, equimolar means the same number of moles, equal moles of both in the same solution, is this a buffer? So go ahead and click in your response, yes or no. We've got 16 responses, 18. And let's see what our results are. We're at 80-20 mix. All right, so most people say that B, this is not a buffer, and 20% of people say yes. Can I hear from, let's start with Sydney Chastain. Did you select this as a buffer or not, and why?
I selected no because I know that HCl is a strong acid. And when you have a buffer, it's going to be either a weak acid or a base.
Okay, so Sydney's pointing out that it needs to be a weak acid-base conjugate pair. HCl is a strong acid, and one thing that she didn't add in there, but I'm going to, is that KCl, when it dissolves, it becomes K plus and Cl minus. Cl minus is a conjugate base, if you will, of HCl, but we know that it's a really terrible base. It doesn't even count as a base. So I concur. This is not a buffer. All right, let's go ahead and do the next one. And these are not in the worksheet for today. I realized that as I was starting my class. So just follow along with these pairings. Couple more seconds for this pairing here. Twenty responses. How many participants do we have today? I think that's about it. I'm gonna close out. So here we're 50-50. How come? Who wants to, let's go for Sydney number 2, Sydney McCann. How did you answer this one?
I know that HNO3 is a strong acid, so I just put no.
Okay. With the knowledge that HNO3 is a strong acid, let's go ahead and repoll. Polls are open. Go ahead and repoll with that piece of knowledge, which you may have had to answer the question in the first place, or you might not have had. A couple more seconds. Closing out. Okay, so what this tells me is that y'all don't know your strong acids. Is that a fair statement? So if we don't recognize something as a strong acid, we're going to be like, that looks like a weak acid. It's something and it's conjugate. But if we know that that acid is a strong acid, we'll automatically say that if it's that strong acid and it's conjugate base, there's no way that this is going to be a buffer. So I completely agree. And this tells me that for next class, you all are going to know all of your strong acids and you're immediately going to recognize them. And we'll be good. Okay, let's go ahead and do the next one. HCl and NH4Cl. All right, looks like we have 23 responses. And I gotta close it out. Can you see my breakout room thing on the screen? No, okay, I didn't think so. I'm setting up breakout rooms for the future. Let's go ahead and check out our responses. All right, we're mixed. We're about 3-to-1 mixture here. Can I hear from Verda? What did you choose and why?
I said no, because HCl is a strong acid.
That's true, but that's only half of the equation. So if it's a strong acid and its conjugate base, for sure, I agree with you. Is NH4Cl the conjugate base of HCl?
No.
Can I have, I agree, it is not. Cl minus would be the conjugate base, but the conjugate base really, it's not a conjugate base, it's so weak. So then we have NH4Cl, not the conjugate base, and HCl. So what do we think? Is this a conjugate acid base pair? It's not a conjugate acid base pair. And in fact, it's two acids. HCl is a strong acid, NH4Cl is a weak acid, because if you put that in water, you get NH4 plus and Cl minus. Cl minus is not a base or an acid, but NH4 plus is a weak acid. So you have two acids. Because it's two acids, this is not a buffer. All right, let's go ahead and do the next one. All right, a couple more seconds. Okay, closing out. All right, we have a 4-to-1 response that this is a buffer. Can I hear from Lauren? Did you choose that? And what's your logic for what you chose?
I said that it was, because if you put NH3, it should take a hydrogen, or I guess so it's a base, and then NH4Cl would split, and you'd have an acid too, a weak acid.
Specifically the conjugate acid of NH3.
Yes.
So you have NH4 plus, which is a conjugate acid of NH3. Okay, which is their definition of a buffer. And especially if you have a 1-to-1 mixture, then we know pH equals pKa as well. Okay, so big picture here was that this was a little bit on the easier side of the questions I'll be asking. And right after our next question, after the learning objectives, I'm going to give some more difficult versions of these. So what I want you all to be able to do is, by the end of class, I want you to be able to describe, we did this last class as well, but how a buffer actually acts to minimize the change in pH when we had a strong acid or a strong base. So we're going to build off of what we talked about last class. And then we're going to do something that's related to the MCAT, or physiological applications, which is using the Henderson-Hasselbalch equation to gain insight into what the molecular composition is in a buffer, in our body specifically. And then we're actually going to do some titrations and look at the specific pH at different points in the titration curve and how to calculate those. And then we're going to look at comparing and contrasting titration curves for weak acid, weak base, strong acid, and strong base. All right, so we got a lot to do today. Are you all ready for like a super intense class? I think the person who I think is most ready is Carter. Carter's like, yeah, I'm ready. Okay. So now let's do a little bit more complicated version of the first thing we did. So I want you to decide if we're going to have a buffer. When we take 1 liter of water, and to that liter of water, we're going to add 100 millimoles of lactic acid and 50 millimoles of potassium lactate. All right, go ahead and do a clicker question for this one. And in the next 1 or 2, I'm going to send us into breakout rooms when they get a little more difficult. Just 16 responses. 21 responses. All right, I'm going to go ahead and close this one out. And I'm going to ask for Samuel to describe what he chose and why.
I chose A. I honestly wasn't sure, but I was pretty sure that lactic acid was not a strong acid and that potassium lactate would act as a buffer. So that was my guess.
All right, so I want to take what you said and build on it. So you said that lactic doesn't sound like one of our strong acids. And if we are really confident in our 6 strong acids, we'll agree with you and we'll say that's not a strong acid. We also know that it's an acid because it has it in the name. So that's really nice, right? And then can someone else help build on what Samuel said as far as why combining lactic acid with potassium lactate would make a buffer? Anyone willing to?
Is it because of the conjugate base pair?
Yep, can you elaborate on that?
I'm not really sure, I'm sorry.
Okay, so I'll help with some terminology. So the idea of 8 at the end in chemistry usually means a negatively charged something. And so lactic acid, the conjugate base is lactate. And so that 8 refers to a negatively charged compound. So this, when it goes into water, the potassium will separate because potassium is a positive charge, lactate is a negative charge. And so this is going to end up making a buffer, and the buffer is going to have 50 millimoles of our base, 100 millimoles of our weak acid. So using the Henderson-Hasselbalch equation, if we knew the pKa of lactic acid, we would be able to calculate the pH of this buffer. All right, let's go ahead and, so I agree with the majority of class on that one. Let's take a look at the next option. So now we have lactic acid and HCl. Go ahead and click in your response. All right, we're getting there, 22 responses. I'll go ahead and close this out. Can I hear from Kevin? What did you choose and why?
I chose no because HCl is a strong acid and plus they're both acid.
Great, and lactic acid is a weak acid, 100% of the class agreed with you. This is not a buffer at all. Okay, so now let's talk about a solution of lactic acid and sodium hydroxide. So for this one, I am going to send us into breakout rooms. So I'm going to go ahead and open those now, although I'm going to move a couple of people just because the rooms are uneven. Let's do this. Okay, I'm going to go ahead and open. They're a little bit bigger breakout rooms, so please try to ask questions if you're trying to work through this and you don't understand where people are getting to. See you in a minute.
You're muted.
Why does it mute you now? This is like a new setting where it mutes you when you come back from the breakout room. I thought I was on it. I was like, I'm totally sharing my screen. I'm not forgetting that because Amber's pointed it out to me last time, I guess. How confident are we in our answers to this question? Very confident? Me, not so confident. Okay, I see a bit of a mix. Patrick's dog's giving us a thumbs up. Okay, almost everyone's back. So let me hear from someone that was not in my breakout room. Sarah Ray, would you be willing to share your group's discussion and answer?
We were talking about how the ratio is off, the 3 to 100, and the NaOH is a base.
Okay, those are all very important components. So can I get anyone else that wants to build off of that? Maybe Stacy, would you like to build off of those statements on how to decide whether this is a buffer or not?
Is it because NaOH is a strong base and also it's not a conjugate acid base pair?
Okay, I think everyone was pretty confident in saying we have a weak acid and a strong base. It is not a conjugate acid base pair. So by that definition, it's not a buffer. But did anyone then go into what happens when you put a strong base with a weak acid? Did anyone discuss that in your groups? Bueller? Bueller?
No, we did not discuss that.
So maybe if we have a lactic acid, I'm just going to write a weak acid, right? And we have hydroxide. What do you think they do when they hang out next to each other? Taylor, do you mind going on since you were brave enough to volunteer?
What happens if they hang out with each other?
Yeah,
With
because
the
a weak acid and a strong base, or just
with the strong base, like completely consume the weak acid.
and in this case, you have 100 millimoles of your weak acid. You have 3 millimoles of your strong base. So which one's going to run out first?
Oh, would it be the? Oh, the weak acid would run out first.
So if you have 100 of them and 3 hydroxides, you're going to run out of the one with 100 first?
Well, I thought it was because you have to have a 10-to-1 ratio if it's a strong acid or base. So,
So there's, maybe let me interject. There's two questions you need to ask yourself.
okay.
First, do you end up with a mixture of a conjugate acid base pair? If the answer is yes, then it can be a buffer. The second part is there enough of both of them to be at least 10-to-1 ratio, if not closer to 1-to-1, in order for that to really be an accurate buffer and to use a Henderson-Box to calculate the pH. So that first question is there a conjugate acid base pair? And I think that if we look at this, we're going to use up 3 millimoles of each of these. Started with 0 of A minus, but then we made 3 because every hydroxide consumes 1 weak acid. So the answer is, in the end, we don't have any strong base left. Remember what we talked about last class. Anytime we have a strong acid or strong base, if it's in the presence of the other one, whether it's weak or strong, it's always going to react until it's completely used up. So this was an example where we do have a neutralization reaction occurring, and that neutralization reaction uses up a portion of our strong acid, not all of it, because we don't have the same amount, and it uses up all of our hydroxide. So in the end, we have 0 OH minuses left. So we have a mixture of HA and A minus. So based off of that, we have a buffer. So I think most of the people answered no because they didn't think that we had a conjugate acid base pair mixture. But based off the discussion we just had, it should be a buffer, right? Does anyone argue me on that?
Wouldn't it just be like a really crappy buffer?
So what does that mean?
Like it would not buffer a lot at all?
And in fact, we couldn't use a Henderson-Hasselbalch to calculate it because it has less than a 10-to-1 ratio. And by our definition, we kind of say a buffer has to be that 10-to-1 ratio. And so for that reason, I would actually say that technically it has the components, the weak acid, weak base conjugate pair, but it doesn't have enough of either one. And so what Carter says is exactly right. It's a really crappy buffer. It has very low buffering capacity. So I would actually call this not a buffer. Not for the reason I think most people answer. Most people I think said it's not a conjugate acid base pair, but it is. Instead, the ratio isn't high enough. We need a lot of both in order to be a good buffer. Questions on that before I move on? Feel good about that? Let's go ahead and do one more of these. I'm going to send you into breakout rooms again, and we should be back together and probably be able to go through this one a little bit quicker. All right, we got almost everyone back. All right, we are not in agreement on this problem. So can I hear from Kelly what discussion you had in your group? Oh, did I just lose Kelly? Or is she back? Is Kelly there? Dang, where is I called on her? All right, Gabby, you've been relatively quiet in our group and otherwise. Would you mind sharing kind of how we talk through this and how you think about it?
If I'm correct, we know that HCl is a strong acid, so it will dissociate completely. And so ammonium will bond with that chloride, and then like it will just leave the conjugate acid of ammonium?
I'll be a little bit careful with your terminology there. So you said ammonium, and ammonia is the base, and ammonium is its conjugate acid. So just be really careful that we're using ammonia if we're talking about the base form of that, okay? So just a little nuance. And so this one in particular is saying that we have a weak base in solution, and we're adding to that a strong acid. So if we have both of those, we know bases, they accept protons. Strong acid, react until it's gone. And so here we have a chemical reaction that when we combine those, I'm gonna give myself a little bit of space down here. NH3 plus HCl yields NH4, maybe I can separate this out, plus NCl minus. And in this case, we started with 75 millimoles of each of these. So all of these gets used up and converted into NH4 plus. So Jesse, what do we have left in solution after these two are combined?
Say that one more time, Dr. Bailey.
What do we have left in solution after both of these are put in solution together?
Well, you're going to have, I think you'd have a little bit of ammonia, a little bit of ammonium, and there'd be some extra hydrogen ions.
All right.
Right.
Does anyone disagree with Jesse? Can I hear from someone that disagrees with Jesse?
I disagree. All of the ammonia and the hydrochloride will be used up, and we will be left with just the conjugate acid of ammonia, which is the ammonium, and the chloride. Yeah. Ammonium chloride.
Yep. So after this reaction is complete, it was a limiting reagent problem, if you will, and we used up all of the HCl in that process. We also used up all of the weak base. So now, since we only have a solution of NH4 plus, can we use the Henderson-Hasselbalch to figure out the pH of this solution? Thumbs up for yes, Henderson-Hasselbalch. Thumbs down for no, Henderson-Hasselbalch. What are we gonna use Henderson-Hasselbalch? Yes, no.
Hey, Dr. Bailey. So I was thinking that because ammonia is a weak base, that it wouldn't pick up all the hydrogen off the hydrochloric acid.
So that's a really good point, Jesse. That weak bases will not pull protons off of water and completely ionize their conjugate acid. But if you put a weak base, any base, in the presence of a strong acid, that strong acid is what drives the reaction. So that strong acid will protonate every single basic site until there's no more strong acid left. So it's really more of a function of your strong acid. If you ever see a strong acid, that reaction is going to completion until you use up all of the strong acid. Does that help clarify that point?
Yes, sir. I knew that the hydrochloric acid would completely dissociate. I just didn't realize that.
I think we can add to that. I've heard that a couple times, that strong acids or bases completely disassociate, but I also want everyone to say it completely disassociates and it completely reacts. Both of those are true when you have a strong acid or a strong base. So because we had the exact same amount of our strong acid and strong acid and weak base, then all that strong acid has to get used up. So afterwards we have none of that weak base. So in this case, we only have a solution of NH4 plus aqueous. It doesn't count as a buffer because we only have one of the conjugate acid base pair. So we cannot use Henderson-Hasselbalch. So how do we find the pH of a solution that is only NH4 plus? Amber, how would you find the pH of that solution if we can't use the Henderson-Hasselbalch equation?
I don't really know.
Who has an idea how we'd find the pH of a solution of only NH4 plus? I'll give you a hint. Think back to
Should you do
What's the Ka?
we could find the Ka. I can give you the Kb. And I heard someone else starting to speak up. Who is that? It's the female voice.
I was going to say we could use the pKa of the ammonium ion that we get, and then add it to the log of 1 over the ammonium ion, but maybe that's not right.
Well, so careful. If we do 1 over, we're saying 1 is the concentration of our weak base. In this case, we don't have the weak base, so we cannot use the Henderson-Hasselbalch equation, which is what you were describing, I think. So if we can't use the Henderson-Hasselbalch, we don't have any concentration of ammonia to start with. How do we find the pH of a solution of a weak acid if, like Jesse said, we knew the Ka or Kb?
Would we do a rice table in that case?
If we ever have a solution of only a weak acid or only a weak base, to find the pH, we have to use an ice table or rice table, however you want to describe that. Absolutely. Okay, so we're going to do that in a minute. So before we do a whole bunch of calculations about pH and with titrations, we're going to do 2 more exercises. I'm going to go ahead and close that down. So last one, I think I didn't answer that one. Last one was not a buffer. Go back. So I'm going to do 2 things. This question is about, it's a question that's actually asked on the MCAT very frequently. So we're going to take this question about someone exercising, and we're going to try to decide, just based off of pH alone, what we have more of in solution. So after exercising, we all know that we build up lactic acid in our blood. And I gave you the pKa of that acid, lactic acid, which we've been talking about, and the structure is shown below. Assuming that we have standard physiological pH, what would we expect? More lactic acid, more lactate, the anion, the conjugate base, or would we have an equal mixture of both of those? So let's do a 1-minute breakout room on this one. And I want you to really think about why, and you might want to think about the Henderson-Hasselbalch equation. All right, we got almost everyone back. All right, we are not in agreement on this answer to this question. I haven't asked Samantha to answer a question yet. So can you describe, Samantha, what your group discussed? If you have audio capabilities. maybe. Looks like Samantha maybe isn't able to respond. Can we have Aislinn? We haven't heard from you yet today. What did you group discuss this question? How do we answer this?
Have we discussed that since it said the blood pH doesn't change, then we know that the pH is like 7.4 or something like that? I didn't know the exact number. 4 or 5. So we can plug that into the Hasselbalch, that one, which is,
Anderson-Hasselbalch, right?
yeah, sorry. pH equals pKa plus log of the concentration of the base over the concentration of the acid, which we don't know.
Okay.
And
so
then,
what can we infer from that?
I didn't know where to go after this part.
Okay, so yes, mathematically you can solve for what that ratio is. Totally cool, fine. It's going to be either bigger than 1, smaller than 1, or equal to 1, and then you'll be able to figure out that ratio. I want us to use logic to discuss this. So if pKa is 3.0, if pH was also 3.0, what would the ratio be of lactic acid to lactate? Which one would we have more of, or would we have the same of both?
Have more of the lactate ion.
So if we had a pH of 3.80, that was actually the first question. Which one would we have more of? So if pH equals pKa, if we have pH equal pKa, we have more lactic acid?
Yes.
I think there's more.
Everybody, I feel like we had class on Monday, but maybe people don't remember it. When
Do we not
was
have the same amount?
Exactly. pH equals pKa means we have an exact equal mixture of a buffer. So is the pH higher or lower than pKa in this case? Higher or lower than pKa? Higher. pH is 7.45. So does that mean we have more of the base or the acid in the conjugate acid base pair?
We have more of the base.
Absolutely. So that's the level I wanted you to get to in this problem. Yes, mathematically you can then solve that, but you can solve the actual ratio of those, and I think it's about 1,000 to 1 or 10,000 to 1 more of lactate than it is of lactic acid. So I think that this is not an intuitive answer. I think most people, oh, you exercise, you have lactic acid in your blood. Of course, there's more lactic acid than lactate, but that's not true. If it was true, our pH would be below 3.8, which would mean we'd be dead. Because if your pH alters more than about 0.2 or 0.3 units from healthy pH, then you go into shock. So if it's acidic, it's called acidosis, and that's a really toxic condition. Your body starts to fall apart. If it's too basic, pH is above 7.45, then that's called alkalosis, and that's also a very detrimental condition to be in. So this is literally a question pulled out of MCAT exams, and so I thought it'd be useful to kind of think about how we can apply the Henderson-Hasselbalch to figure out what ratio over conjugate acid base pair we have. All right, and I think I have this all worked out. You can go back and look over mathematically how I solved for that. It looks like about 3,700 times more lactate than lactic acid is what I solved. Okay, now we're gonna skip down to the next part of our worksheet. So I want us to start thinking out about titrations again. So as a titration we're talking about, and we're gonna go through these relatively quickly. So I'm gonna call on people individually. I want you to think about what is this, there's 3 points that I want you to think about. If you have initial solution, is it, what pH is it? when you have a equivalence point, what is the pH? And what is the pH at the half equivalence point? All right, those are the three questions. So the first one is when we have a strong acid in solution, and we're going to titrate that with a strong base. So you can see that the volume of hydroxide or strong base is on the bottom here. So what is our pH? If we have, let's ask three questions. What is our initial pH when we have a strong acid as our solution? Is it above 7, equal to 7, less than 7? Where are we at? Aislinn's pointing down. Can you just say audio what you mean?
It's a strong acid, it's below 7.
Okay, and depends on the concentration, it's probably going to be far below 7. When we add enough of our strong base to reach the equivalence point, what is the pH? Go ahead and click in what your pH will be when you reach the equivalence point, when you start with a strong acid like HCl and you titrate it with a strong base like sodium hydroxide. Couple more seconds. By the way, if it looks like I'm playing with my phone, it's actually the Reef app. It's just a way I can cheat and see the numbers before I pull it up on the screen. Couple more seconds. Closing out. Okay, overwhelmingly people are saying that this is a pH of 7. Can I hear from Carter, why would the pH be 7 at the equivalence point of this titration?
I think they both would just kind of meet in the middle. You get a strong acid and a strong base, both with high pHs and low pHs. They were just 7's neutral.
Okay, fair. That's a good relative statement. Tina, can I have you add to that maybe why we would have a pH of 7 when we started a very acidic solution and we're titrating out the strong base at the equivalence point? Why is the pH 7?
I was thinking kind of the same thing. I was thinking if it's really acidic, then it would be below 7. Well, depending on the concentration, and if it's really basic, also depending on the concentration, it would be above 7. So if we're at equilibrium, we met in the middle, I also said it would be 7, like neutral.
So something that I want to make sure to clarify is that equilibrium, a term that we've been using so far to kind of talk about a weak acid giving up some of its proton to water, or a weak base taking some of protons from water, that is not the same thing as the equivalence point. And this is something that's really common to mix up. So equivalence point, what does that mean? Who has a good definition of equivalence point that we can use? Because we're talking about titrations, and equivalence point is probably the most important feature of a titration. Someone's got to be very confident in this definition. Anybody? No? You've been tracing for weeks. You don't know the definition of what your endpoint is, your equivalence point? All right. I see a lot of faces that look maybe like they probably should know, but they don't. Let's set that straight. Okay, let's do that. The equivalence point is when you have the exact same number of moles of both of your components, if it's a 1-to-1 ratio. So if you started out with 1,000 moles of your HCl, the equivalence point is when you have the exact same number of moles of your titrant. So remember, we called it analyte. The one that starts, that's the one that's in the solution you're analyzing, right? You're analyzing it. And you're saying, when I get an equal number of moles of the titrant, the thing that I'm adding in, right? I'm adding it in over time. When I get the same number of moles, I have an equal number of moles of my analyte and my titrant. And if we, maybe in the beginning, this is a big question mark. We don't know how many moles of HCl we had, but we know that we added 1,000 moles of our titrant. We can say, well, it's a 1-to-1 ratio. So then I know how many moles of my analyte I started with. So titrations are actually a really cool tool. It says, if I know what the chemical reaction is, and I know the stoichiometric ratio, I don't need to know how much I start with of one, because I know how much of the other I added to get to the equivalence. And the equivalence point for strong acid, strong base is always going to be a pH of 7. Why? It's a pH of 7 because if you have 1,000 HCl's and you add 1,000 sodium hydroxides, afterwards, the only thing you have left is water and sodium chloride. Water is a pH of 7 by itself. Sodium and chloride have no impact on the pH. So when you're done titrating a strong acid and a strong base, you have a pH of 7, it's neutral. Okay, so the equivalence point is always when we've used up all the analyte with the titrant. So maybe we weren't super confident in how we got to that answer, but I agree with the majority of the class. pH is 7 when you have a strong acid being titrated with a strong base, or a strong base being titrated with a strong acid. And so what that titration curve looks like is, depending on the concentration of our acid, we're going to start strongly acidic, a low pH. In this case right here, the number of moles of hydroxide we needed to add, which we could figure out from the concentration and the volume, right? We would have volume times moles per liter, which is our molarity, remember? We know the volume and the molarity, we can find the number of moles. That is exactly the number of moles needed. And when we are completely used up with all of our strong acid, that's that inflection point right there. We have a neutral pH because the only things we have in water are sodium hydroxide, or sorry, water and sodium chloride. If we go one drop past, now all of a sudden we have a very basic pH because now there's only water, sodium chloride, and sodium hydroxide in solution. So the sodium hydroxide is free to just be sodium hydroxide. It's going to be a really basic solution, and any more sodium hydroxide we add is just going to make it more and more basic, closer to the pH of the strong base by itself. All right, so let's take that, and now let's think about the titration curve for a weak acid with a strong base titrating it. And once again, going back to Jesse's point he asked about, a weak acid or a weak base is not going to completely disassociate, but whatever strong base we add to the solution or strong acid, those are always going to get completely used up. So go ahead and draw, I think you have 2 more boxes in your worksheet there. Go ahead and draw what the titration curve would look like for a weak acid titrated with a strong base and a weak base titrated with a strong acid. So think about what's the initial pH. Let's assume the concentration is the same. So if we have the same concentration as we did with our HCl, is the pH, the starting pH of a weak acid going to be lower, higher, or the same as a strong acid? If we had 1.0 molar, maybe of both. Would the pH be slightly higher, the same, or more acidic than a strong acid? What do we think?
It'd be a little higher.
Why?
Since it's a weak acid, it wouldn't have as low of a pH.
Fantastic. Okay, so that's your first starting point. So go ahead and draw what you think that titration curve looks like. You should have 3 boxes there. The first one is a strong acid with a strong base. Second one is a weak acid with a strong base. So think about the pH is going to start maybe a little bit higher than a pH of 1 in this case. What is that inflection point? What is the equivalence point going to look like? Is it going to be 7? Is it going to be higher? Is it going to be lower? And then the same thing with a weak base. So I'm going to go ahead and give you all a minute. Do you want to do this in breakout rooms? Thumbs up for breakout rooms to talk through this. Thumbs down for we can just do it here. I see more thumbs down than thumbs up. I see a lot of people that aren't. Okay. So go ahead and work on drawing those curves. Draw it in pencil. We'll come back. We'll kind of draw over it, but put something, please put something down, or at least think about what is the initial pH, what is the pH halfway to equivalence point, what is the pH equivalence point. Let's do another 30 seconds to kind of pencil in what they might look like. Okay. So let's go ahead and we'll do this as a series of clicker questions, and then we'll draw out the curve afterwards. So the first clicker question is, okay, we have a weak acid, just a weak acid in solution before we add any of the titrants. So remember, this is our analyte. This is the thing in the beaker that we're starting with. We're saying we're analyzing this. Is the pH going to be greater, less than, or equal to 7? You all see the clicker question up? Couple more seconds to get your clickers submitted. Closing out. Okay, we have a mixture, but if we're saying we only have the weak acids before we add any titrant at all, this is definitely going to be an acidic solution. All right. So we start out with none of the titrant being added. That's on the far left side over here. That means we're going to have a pH that's less than 7. Depending on the concentration, we're going to say it's acidic, but maybe it's not going to be as acidic as a strong acid would be by itself. All right, so then the next question is, when we add some titrant, those problems that we just went through, right? We said we're going to take some of that weak acid and we're going to put it in the presence of a strong base. So that means that some of the weak acid is going to get used up. When that strong acid, some of that weak acid gets used up, we're saying that we're taking some of that weak acid and we're converting it into a weak base. So once that has happened and we're halfway to the equivalence point, half of the weak acid has been used up and converted to the conjugate base. So what do you think the pH is going to be when we've used up half of the weak acid? So now we have an equal amount of our conjugate acid and conjugate base. Couple more seconds. We don't know. What do we know about the pH of the solution when we have an equal amount of a conjugate acid and base pair? Anybody? Equal amounts of conjugate acid base pair. Kat, what do we know about the solution, the pH?
Shouldn't it be neutral?
It's neutral if we only have a salt and water. But
Gotcha.
we're saying we have a weak acid and its conjugate base. So pH equals pKa. It's a buffer, okay, right? It's a conjugate acid base pair. So in this case, if we're defining it as a weak acid, that solution is still going to have a pH equal pKa. And if it's a weak acid, the way that we define a weak acid is that pH equals, the pKa is lower than 7. The pKa is higher than 7, then technically it's kind of semantics, but that means it's the conjugate acid of what we consider a weak base. So you can either say you have a conjugate acid base pair, that's the acid is really the one that's it's an acid and we can find its conjugate base, kind of like lactic acid and acetate. That's really a weak acid and its conjugate base. pKa, that would be less than 7, right? 3.8. If we have ammonia in ammonium, technically that's more of a base and it's conjugate acid. So the pKa of that's going to be above 7. All right. So then after we have added, like we just did in that last problem, when we have used up all of our weak acid, We have completely titrated it. We're at the equivalence point. The only thing we have left in solution now is that weak acid. That's it. What is the pH of that solution going to be? And think about this from an standpoint of, if we only have a weak base in water, is the pH going to be equal to 7, greater, or less than 7? A couple more seconds. Closing out. Confidence high, confidence low. Give me some thumbs up. Feeling somewhat confident in this. I see a couple of medium thumbs. Yes. Okay. We're definitely going to have a basic solution because all we have is a weak base in water. How do we find the pH of the solution? Are we going to use a Henderson-Hasselbalch to find the pH of the solution? Sydney McCann, would you use the Henderson-Hasselbalch to find the pH of a solution of conjugate base in water?
No.
How would you find the pH of a weak base in water?
An ice table with the KB.
Absolutely. Ice table with the KB. Thanks, Tracy, for stepping in. Okay, so this is the part of the titration graph where you have some level of both, right? We started with only weak acid, and then as we went across, we converted more and more of that weak acid to its conjugate base. When we got to this volume right here, the pH was equal to the pKa, we had a 50-50 mixture of the conjugate acid base pair. As we kept adding more and more base, though, we kept converting more of the weak acid into its conjugate base. And so we got more and more basic again until we used up all of the weak acid, and the only thing we had left was a conjugate base in solution. And after that point, if we keep adding strong base, then we end up with hydroxide only in solution. And so our titration curve would look something like this. We start out with an acidic pH, we become more basic, pH equals pKa. When we've used up exactly half of our conjugate of our weak acid, we can now find pH equals pKa. Please tell me you've done this in lab. So in lab, you find where's your equivalence point? Where did that big inflection end up? And then you say, that's my equivalence point. That's when I've used up all of my weak acid, and the only thing I have is weak base. So if I go back half the number of moles, I know that that is when I had a 50-50 mixture where pH equaled pKa. Does that sound familiar at all?
Yes, we're working on that right now in Mr. Sweeto's lab.
Okay. So this is why. A lot of times in lab, it's so easy to focus just on like, what are my numbers? How do I calculate it? But hopefully this helps you wrap your head around. If I know how many moles of OH minus it took to get to that equivalence point where I used up all of my reactant, I can figure out what was half of that, and that was where pH equals pKa. All right. And then from that pKa, you can look at a table and say, well, there's only one acid that has a pKa value of this. And you can identify the acid from that. So that's kind of what your labs are doing. Okay. If we have, let's talk about a weak base. Should we do these quicker questions, or maybe it's faster if we don't? Let's not do them as quicker questions, but you can do thumbs up, roll, thumbs down. Are we okay with that? I need everyone to participate though that I can see. All right. So if we have a weak base in solution, think of NH3, think of pyridine, whatever these weak bases are. Is the pH going to be greater than 7, equal to 7, or less than 7? Okay, we have only a weak base in water, and we have most people doing thumbs up, but some people doing thumbs down. So can I get Taylor McCann? What did you answer and why?
Are you referring to me?
Yeah, I mixed the two names of the two people sitting next to each other in my window. Sorry.
Okay.
Taylor,
You're
Taylor
okay.
Gamble.
Okay, I said A greater than 7 because if you're starting off with a base, even though it is weak base, it still is going to be greater than neutral, which is greater than 7.
Exactly. Okay. So if you ever feel flustered and confused, just go back to the basics. Basic, haha, dad joke. It's a base, it's in water, it's gonna be basic, okay? If it's an acid in water by itself is gonna be acidic, all right? So it sounds really simple when you say that, but sometimes you kind of get lost in like, oh, but what are the calculations and how, so don't worry about that. Try to just go back to the basics. Okay, when we get to the point where we have a mixture of a conjugate acid base pair, and it's technically a base, which is really just semantics, but it's a conjugate acid base pair, that's what I mentioned before, that the pH is going to be slightly higher than 7 when pH equals pKa. If you find a pKa value that's higher than 7, what that says is that really we classify that as a base that has this conjugate acid. But really it's semantics. It's really not that big of a deal. When you reach the equivalence point and you have converted all of your weak base to its conjugate acid, is the pH going to be greater than 7, equal to 7, or less than 7? Go ahead and give me the thumbs up, equal to 7, or thumbs down. Okay, I see a lot of thumbs down. Can I get Amber to describe why we might have a pH less than 7 when we're at the equivalence point of a weak base with a strong acid?
I went blank. Because at that point, with the strong acid just kind of overpower is not really the word I'm looking for. I don't know what word I'm looking for, but the strong acid kind of show through a little bit more than the weak base would at this point.
So we want to be careful. I think we used a little bit of this terminology before. In a titration, remember everything that's being added, if it's strong, is being used up. So in this case, the equation is we're adding a base plus, I'm going to say H plus because that's our strong acid. And however many of those there are going to be completely used up to make our conjugate acid. All right. And what we're saying is if we start with 53, whatever, of our weak base, the equivalence point is where we've added exactly the same number of moles of our strong acid. So that means that both of these get used up. And the only thing we have left afterwards, we don't have any strong acid left. So it's not overpowering. It's not about there being any of it left. It's actually all used up. The only thing we're going to have left now is a weak acid in water. A weak acid in water, like we said in the very beginning, a weak acid in water is acidic. End of story. And we can calculate that if we have a Ka of that solution. As soon as we add any more drops, then I agree with you, Amber. If we add 2 more drops of our titrant, which is a strong acid, and now the pH is going to drop way down because now that will overpower. We're going to have a mixture of B plus and H plus. H plus is going to be much more impactful in the pH of that solution. So our solution and our buffer is going to be between the starting point and the equivalence point. So we made a big deal about this 10 to 1, 1 to 10 ratio. So basically that 1 to 10, 10 to 1 ratio is between these two lines. That before this, we have much more of the weak base than its conjugate acid. After that, we have the other extreme, much more of the conjugate acid than its weak base. So this region right here is called the buffer region, where we have a mixture of a conjugate acid base pair as the base is being converted to its conjugate acid more and more. And in the middle of that is where pH equals pKa, and we can learn what the identity of weak base is. Same exact thing is true of the weak acid that we titrated, that middle section right there, where we have a mixture of a conjugate acid base pair, that is our buffer. And so you can make a buffer either by just pouring those two things together, salt of the conjugate acid base pair, or you can make it through a titration. So the last thing I really wanted to do, but took a long time, is actually do some calculations of what we exactly talked about. So maybe we can do the concept of it really quickly. So let's talk about a specific example here. So if we have a solution, and I just always use acetic acid because it's easy to do. We have a solution where we have 50 milliliters of a 0.1 molar acetic acid solution. And we're going to titrate that with a strong base. Before we add any of the titrant, we're just talking about our analyte that is just acetic acid. How are we going to calculate the pH of that solution? Go ahead and click in which one of these three is the approach that we would use to calculate the pH before the titration begins, before any strong base has been added. Couple more seconds. Closing out. All right, I'm very thankful to see that the majority answer chosen was an ice table. And can I hear from, let's see, Sarah Ray, why we would choose an ice table to calculate the pH of this solution? I think you're muted.
In the moles of it, so you need to, I'm not sure.
All right, so for the sake of time, I'm going to add in. So if we have a weak acid in water, and that's it, it's not a buffer, right? We can't use Henderson-Hasselbalch because it's not a buffer. It's not a strong acid, so we can't just take the negative log of the concentration. So we have to use an ice table in order to find the pH of a solution of a weak acid. So we could calculate the pH. I think we did this before. We use an ice table. We can do that calculation. Then in order to find the pH, once we titrate it, so now we're going to add a little bit of sodium hydroxide. How are we going to calculate the pH of that solution? Are we going to use an ice table? Henderson-Hasselbalch, do we need to do stuff before? How do we do that? Does anyone want to pipe up or share? Or do you want me to talk through it? Does anyone
Just need the Ka, Dr. Bailey. Oh, there it is. So you'd set the Ka be equal to the concentration of the acetic acid, and then well, the concentration of hydronium squared over the acetic acid concentration.
Okay, so for the first one,
for the hydronium ion concentration.
I agree, before we added the titrant. But after we add the titrant, so we're saying we're adding some sodium hydroxide to the solution.
Oh.
And so we have to think about how many moles of each do we have. So this is where we use that ICF table that I talked about really briefly last time. You can do however you want. We need to find the limiting reagent. So we know that in this solution, 50 milliliters or 0.100 molar, we had 5 millimoles of acetic acid. In this solution of sodium hydroxide, we have 1 millimole of hydroxide. Each strong base is always going to be used up. And so we're going to say we're going to use up 1 millimole of our acetic acid to neutralize this hydroxide and make sure they're both gone. In doing that, that 1 millimole of acetic acid forms acetate and uses up 1 mole in the process of our weak acid. So in the end, we started with 5 millimoles of acetic acid. We only have 4 left because 1 of them was used up. We started with no acetate. We gained 1 because that was a converted. And so now we have 1 millimole here. So how do we find the pH of that solution? Anybody? Last real question of the night.
Henderson-Hasselbalch.
Henderson-Hasselbalch. We have a buffer. We have a mixture of 1 of the base to 4 of the acid. That's within the range. That's a buffer. So we can use a Henderson-Hasselbalch, and pH is 4.138 we find through that. pH is still going to be more acidic than pKa because we have more of the acid than the base. And so basically what we're saying is we added hydroxide to an acid and water, converted a small amount of that to the conjugate base. We ended up making a buffer, and we can calculate the pH of that. So you'll see on that sheet, it has a couple more points in the titration. I really advise try to work through those before class on Monday. I think that's what our homework does as well. Post questions on the Blackboard discussions. If you have any questions, post them. And then I'll be there to answer your questions, or you can set up a time to meet with me if you'd like. But that is our class for the evening. So I hope that you got a bit of a feel of exactly what a titration is, how to do some of those calculations, and then we'll do more of those in our class on Monday. I believe that this is our actual learning objective. So look through these, and the thing that we didn't quite do was this third one, find the pH of various points in a buffer. All right, hope you have a good night. I'll stick around for a few minutes in case you wanted to talk through some of those other points or chat.
Are you available for a not tutoring session, but a office hour tomorrow at all?
Yes, and I'm trying to get this recording to stop. Sorry.